and the video that you've probably been waiting for, which are the tips, tricks, and shorthand for doing electron configurations. Now, one of my favorite tips and tricks is to use the periodic table. So the order of filling follows the periodic table. And you will see this in the way that some periodic tables are like given colored backgrounds. So the example, like the way that the colors are shown on this periodic table, everything that's in pink is kind of referred to as being in the S block. And what that means is that the very last electrons that you look at are going to be in an S orbital. Now, if you are maybe kind of noticing a little more, it's only 2 columns wide. There's only one S orbital in each set, and each S orbital can only hold 2 electrons. So, let's grab some random examples and see if this can start to show you the pattern. So, we did hydrogen, that was 1s1. Helium, we also did, which was 1s2. Now, if I were to do lithium, 3 electrons, I would fill the 1s, and then the next level that I fill is 2s. So lithium ends in a 2s1. It's in the second row, which is n equals 2, and it's in the first column, which means it ends in 1 electron in that s orbital. So as a configuration, it would end in 2s1. In sodium, I'm going to end in 3s1, which the example that we just finished at the end of the last video, we ended with a 3s1. Now we had to fill a bunch of stuff in between, but right where it is in the periodic table can help you figure out what the end of that electron configuration should look like. And also, it can kind of help you remember the orders of the energies. So what I like to do, and as you can see here labeled, the green block, that's labeled as the P block. So count the number of columns that are in green. There are 6. And you can fit 6 electrons in the set of 3, the 3 p orbitals at each level. And it's 6 columns wide. So if I'm putting electrons into boron, where it's in the second row, it's the top row, but the first time that I see a p orbital is at n equals 2, so that works out perfectly. So 2p1 is what my boron configuration would end in. We did see carbon, which ends in 2p2, nitrogen would end in 2p3, and so on. You will be able to count across the periodic table to do these electron configurations. Now, do notice something weird about the transition metals. That's not so weird when you remember the energy orders. So if you look at row 4, right, we're expecting n equals 4, but after calcium, when you go to scandium, this set, the set of transition metals, it's labeled as the D block. This is 10 columns wide, and the D orbitals, that set of 5, will hold 10 electrons. Interesting coincidence. It's not a coincidence. The first occurrence of the D block is in row 4. Now, the first occurrence of d orbitals is at n equals 3. So when you are looking at these electron configurations, first of all, when you get to potassium and you count 4s1, 4s2, if you were continuing to count and look at scandium, that's going to end in a 3d1. The principal quantum number changes when you go into that transition metal row. But also, we went from 4s to 3d, which if you go back and look at that energy ordering diagram, the 4s was lower in energy than the 3d. So we would fill it first, and the periodic table reflects that. Okay, We can do as many more examples of this as you want. I want to talk about another way. So I really like this method. Another way that people really like to remember the ordering of the orbitals is with this kind of like arrow drawing method, where if you write all of the s orbitals, so 1s, 2s, 3s, and then the p and the d in columns, you can just draw arrows that like angle down to the left that will give you everything in order. So my first arrow runs into the 1s, I fill the 1s. My second arrow runs into the 2s, I fill the 2s next. Then I run into 2p, and then 3s, then 3p, then 4s, then 3d, right? So that's going to give me that ordering just right. So it will give me the 3d before the 4p, but after the 4s. Once we have these electrons in specific places, we can start to label them as different types of electrons based on where they are. So this is where we label valence and core electrons. And the core electrons we consider that to be anything in an inner shell. We might call it a closed shell, something that's full. So every orbital in that quantum number level has electrons in it. The valence electrons are the electrons in the outermost shell. The valence electrons are the ones that we will care about. They determine bonding, they determine reactivity. As you're starting to see in electron configurations, right, determining reactivity, which is one of the properties by which the elements are organized in the periodic table. Everything in the same column, its electron configuration ends in the same pattern. This is why the valence electrons matter so much. So we will define valence as outermost N shell. I'm being weirdly specific for a reason. And I will ask you about things that it is clear to figure out. That's going to be things that are in the S block and the P block, and you'll see why. So let's look at phosphorus. It has 15 electrons. If I make an electron configuration for phosphorus, it would be 1s2, 2s2, 2p6, 3s2, 3p3. So the outermost N level, the highest number N that electrons are in, is 3. So everything in N equals 3 is considered a valence electron. Everything else is considered a core electron. So everything in N equals 1 and N equals 2 is core. And we would call the N equals 1 shell closed because it's completely full. The N equals 2 shell, right, which is everything with a 2, so the S and the P, is also closed. It's completely full. Now here's the shorthand part. The core electrons, this electron configuration is the same as the electron configuration for neon. So we can do a shorthand for phosphorus that is just neon in brackets plus the valence electrons. Now here's the dig. You can only do this for noble gases. So I could not put silicon in brackets and then write 3s1 for phosphorus. That would look super weird, right? Like or right, 3p1. The 3p is not closed. The N equals 3 is not closed for phosphorus. You can only list a noble gas. So the noble gas that occurs right before phosphorus, I mean, you have to go back right to the end of the previous row. That's neon. The electrons that come after that are 3s2, 3p3. Now the thing to watch out for, and this is why we will deal with valence electrons, but we will be careful once you get below a certain row. So let's do selenium. Selenium has 34 electrons. So filling things in order, it's 1s2, 2s2, 2p6, 3s2, 3p6. After 3p, we go to 4s. So 4s2, then we go to 3d. And I have enough to fill all of 3d. So 3d10, and then 4p4. That's my electron configuration for selenium. Using the definition of valence electrons, my valence electrons are 4s2 and 4p4 because that's the highest quantum number, the highest principal quantum number that electrons are in. This means that my core electrons are everything in n equals 1, n equals 2, and n equals 3. And those are all closed shells. Perfect. Like this is not bad. The weird part that doesn't quite work perfectly, I mean, you still get to use a shorthand, so don't stress about that. But the noble gas that occurs right before selenium, so the end of the previous row, is argon. The electron configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6. So my argon in brackets only takes the place of that part of the electron configuration. So after argon, I have to list 4s2, 3d10, 4p4, out of which only the 4s2 and the 4p4 would be considered valence electrons. So in general, most of the smaller atoms, the things we're going to see, it's valence electrons that occur after the shortcut piece, but it will not be 100% true, so be careful.